welcome everyone to lecture 2 in the Cloud Computing and Big Data course. It's actually a renewed lecture, so we have some new material, of course, some basics of machine learning, which will always remain, and an interesting maybe reflection of the last lecture that we had when we talked about the big view of cloud computing in general. So we thought about the key foundations essentially come from virtualization, come from a lot of elements which have been way before cloud computing existing. So grid computing played into the game, high performance computing played into the game. But when you, let's say, have a 10,000 feet perspective now on clouds, you could say it's always around somewhere having hardware, software solutions, networking, and storage. But one key term is, of course, very important, which is a service character. So what it really differentiated between high performance computing or other, let's say, computing ideas is really everything should be like a service. So easy, accessible, credit card swipe, and then you get basically your services or whatever you need from the cloud. And of course, the paid services is the idea. That's where you get the return of investment. On the other hand, of course, the idea is to get to more and more thin clients, so like these little laptops here. So you don't want to have a big, let's say, server farm in each classroom, do computing there. Instead, you centralize the resources and of course can nicely connect it from the desktops. We were going through many examples the last time, and I mean, many of you know the majority of those. Some are a bit more technically, some are more business character, some are things we use probably daily like Google Docs. But in one way or another, they all are actually cloud services on different levels. And that's something which is, of course, very interesting for us because it has really make our life much more easier. The other element then, or basically the second part of it, was really looking a bit more deeper inside. We've seen here one famous example of this elastic capability. So Amazon Web Services started essentially with the idea of saying we can have computing that scales up and down as needed. Something people called pay-as-you-go, pay-as-you-need, on-demand resources really that are just there, scale up when I don't need it anymore, I can shut it down. And this flexible character turned the coin then also cloud computing, so this elastic idea. Of course, since then, many have followed suit. So Amazon was really one of the first, then Amazon Azure, we have seen here different Google platforms and Google Clouds that all follow suit. Then from the data perspective, this was also interesting. We have seen that big data, of course, is real. I mean, everybody of you will know that these days. But we have also seen that big data doesn't mean always volume, right? The challenge is not necessarily in the volume, it's access. How quickly can I get something into the memory of the computer? How quickly can I get something into the GPU today? So these are all elements where, the velocity matters. And one of the key challenges, if you see here, for instance, is of course then the combination of both, where you have, let's say, 1 petabyte, which is not a problem. But of course, storing 1 petabyte every 20 seconds becomes quickly a problem. So this is another facet where essentially big data and cloud computing converged in so-called frameworks like Hadoop, like Spark, where really the idea was made like really scaling up to really crunch down, let's say, the problems into many different pieces, smaller pieces, and to compute it. And that's what we will do today. We will start with a little bit of analyzing this data with machine learning. Who has used machine learning before? A little bit. Statistics, summary statistics, a little bit. Okay, so this is really an introduction that I gave, I think, 100 times in the last 7 years, and it was really growing on feedback again. And it's really starting with zero knowledge. So everyone who's here in the course and never touched machine learning, don't worry about this. We will build it gradually. And also the basically model we will have today, we keep, let's say, to a moderate degree in terms of mathematics, just to understand then how we leverage Spark basically on this big data. And then in the next lecture that follows, lecture 3, we will then see how that really brings together the scalability of the design. So basically, let's go to lecture 2 material. We will start a little bit with machine learning methods overview. Then we will have basically classification, a specific part of machine learning that we will discuss. And then looking at some of the simplest learning models you can find, the Perceptron, But interesting enough, the Perceptron builds also the cornerstone of neural networks and now deep learning. So in a way, you would have a model which is in the 60s, now very relevant through deep learning. Of course, on steroids and a bit modified, but the key idea remains. There are some different application examples throughout that I will provide, mostly flower classification, but then of course also more advanced classification like food, or basically also going to more advanced models with logistic regression, especially in the second half of the lecture. While the first one is really fundamental, where I bring you really to the key idea, what is classification in the supervised setup. Then the second is rather on really using, the cloud, like we will also do in the assignment. Hence, we had to revise here a lot of things because MS Azure had the insight is not anymore in an educational area. That actually broke lecture 2, lecture 3, assignment 1, so lots of work to be redone, unfortunately. But of course, in a way, it's still existing, but you have to swipe the credit card, right? And of course, this is not what we do with students here, so we had revived everything. But the way how we use the cloud is essentially the same. That's why I want to also make the point in that. We have some evaluation and visualization techniques that we will discuss. But of course, we will have also a practical lecture where I will demonstrate this in the cloud and where we then, of course, can go much more deeper inside this. So fasten your seatbelt for machine learning fundamentals. Often machine learning has a very, let's say, bad reputation. People always think like, oh my God, buy a book and then the first 60 or 100 pages is mathematics, which is most often true. But you can also approach machine learning from certain perspective that's not so complicated and use it. And this is, of course, how we want to do it here in the course. So here is a very specific example today, what I will show you in the first part of the lecture. It's one area of learning called supervised learning. If you remember from one of the first prologue and then also from the lecture 1, the idea that makes it supervised in this idea is to have for all the different data items we have, one guiding label Y. So you can always know when I have here red and green classes, that I know from all these dots that are inside, is it a red dot or is it a green dot, right? This label Y is loaded. If I wouldn't have that, then supervised learning is not really possible. Semi-supervised maybe, but this is really the key differentiator. That's why also supervised learning is by far the most used, because of course it's very clear in the, let's say, outputs, because I can always learn from, let's say, historical records or from old observations, how basically the outcome was in order to potentially predict then something new. And this is what we want to achieve in this, right? The key idea is, of course, not just for fun going through all of them and then create a classifier that knows all the material that is basically inside these classes already. We want to be prepared for the new item, the new data set that is coming, the new unseen data, we call that. And we want to know, is it a red or a green point? And instead of doing this manual, we want to do this, of course, with machine learning. Again, what I also said in lecture 1, if you remember, just briefly, we always need these ingredients, and I come back to this throughout the lecture, right? We always have to assume some certain pattern. Learning something random is useless. If you would have some specific mathematical formula for it, then I would just implement this formula and compute it, right? There's no point in learning what could be a formula or what could be, giving rise to the data. And of course, it goes without saying, machine learning means essentially learning from data. The third ingredient is always data that we need to have. And of course, bring that all together, I will also do in this lecture then the point why we do computing so much. Now, starting with a very simple idea, what could be two classes? You said red and green. Here's one example that is, let's say, one of the machine learning basics. The IAAS classification of flower. It's a specific flower types. And you see already the challenge a little bit for humans is to really tell what type of flower it is. So could someone see exactly what type this flower is here in class, maybe? In all the years, I had one guy who could do this, who was from, I think, bio and flower specialty, but nobody can do it, right? So the idea is now, how can we build a machine learning system that decides that this new flower there is either a Iris setosa or a Iris virginica. Of course, if you go now to a flower expert, he can tell you, looking at this manually, and says, yeah, this is clearly Iris virginica, or maybe it's an Iris setosa. But of course, for us, it's the idea to automate the process. And that's what we're going to do with machine learning. That means we have a prediction task. We want to see new flowers and predict what class it would be, right? So this is something which is for us important. And it's a binary two-class classification problem, a very specific one I put at the beginning of the course. We will come to other problems later, but this is, let's say, the simplest classification problem you can find. You have two classes, is it this or that class? And now the question that you always ask then as machine learner is, what attributes of this flower now is basically helping us? So what attributes in the data? When you classify people in shopping, what is basically attributes of a person that matter? What is the attributes of the flower that matter? So this is always what we ask. And then you come to some observations where you have hopefully some data and where we apply our three, let's say, ingredients. The first one clearly is actually there is a pattern, we believe, because otherwise the people would not have put it already in two classes. However, we don't know what would be the mathematical formula for it. So this is unknown, essentially, which means this is really good for machine learning. And we have some data set already available. There's a UCI machine learning repository with open data sets already a bit tuned for machine learning, which is a learning data set. You see also, I basically subsampled here. It's usually a 3-class problem that I downsampled to a 2-class problem, basically just to make the case here very easy in this class. And when you now think what attributes shape the flower, you see that the petal and sepal, basically the length and the width of those, and you see that here from the Wikipedia image a bit, what actually is a petal and sepal, those actually are very different, apparently, in the attributes in this data set. So in the sense you have the attributes, we call that also features in the data, and then you would have the classes. As I said earlier, we basically have here just get rid of one class and basically just had used 100 samples to make it easy. When you now plot this data, you just take the 100 samples I have there, the 50 I throw in the corner, but the 100 that remain from these two classes, I just put them here, right? This would be just the axis. This is always, let's say, the petal length, and here the petal width, and I plot it there, and you immediately see there's some kind of two clusters that are building, right? But this is, data inspection, data visualization, no machine learning so far. But we see already our assumption confirmed that there's a pattern. Apparently, the petal length and petal width is small for some flowers, and actually it's quite large in others. So this gives us, let's say, an angle to think about what machine learning models could help. On top of it, which is nice, someone already had used this 100 samples and said, this is the Iris setosa, and this is the Iris virginica. So we call it labeled samples, right? This is now this Y that you see. So we know exactly that these are specific types of flowers. And with this, we can get going for machine learning in a supervised fashion. Supervised because the label always gives us the importance of thinking about, are we correct, classified or not? Now, we talk about this as a very simple setup. We call this linear separability, which means, in other words, maybe it's possible to find some line in between that determines either your Iris setosa or Iris virginica. And this is now what we want to create, to develop with machine learning. And the point is, of course, we don't know how this line is and where it should be, right? We can, of course, do it now manually by plotting, but we have no idea if new samples come, if they really will be still correct. So we find an automatism that really differentiates them both. Of course, in practice, when you go in real life situations, often the classes are intertwined, linear, inseparable, and we will discuss it later, what trouble it causes. But here, that is really the simplest assumption you can have. We could potentially create a line that gives us a so-called decision boundary, how it is called in machine learning, to say everything above this decision boundary is this class, everything below this decision boundary is that class, right? So still, this is something we had no algorithm so far, nothing on machine learning, just an idea how that actually could work. Now, when we think about how a line from basic mathematics looks like, we remember a little bit, of course, the equations. And what we want a little bit is to find a threshold where we can say everything below or above is essentially this or that type of a flower. Now, the point is, and that's why I marked it red, these are unknown, right? So when you basically have the idea of weights that we established, and basically, if you think about what the weights or coefficients do for the line, right, or plane, this is something, of course, which we have to learn. That's why we mark it red. And also the threshold, if you remember, where basically is this line somewhere in the space, this is also something what we have to learn. Now, the beauty is we have X. That's a constant, right? In our case, it's a data set. We have many different 100 samples of flowers we always can stick in. So essentially what machine learning is now do, using the attributes of the flowers that we define and find this decision boundary that if you actually satisfies these two equations, right? Now, the idea what in the 60s someone came up at the end basically of the 50s, but 60s roughly, was Rosenblatt then with the so-called perceptron. There's always a model and an algorithm. This is a perceptron learning model, and there will be a perceptron learning algorithm. But this is a model, maybe the simplest learning model you can find, where you again come back to our basically idea what we just had with the line, right? And would say we just have all our data set, we put it in, and it's modeled around, let's say, a neuron where you have the strength really of all the input signals, then either, let's say, more enforced or less enforced. So you learn the weights, essentially. You sum up linearly. That makes it a linear learning model, right? You sum up linearly and then put it to some form of a function. This function is very loaded. We will talk about this many times. Linear regression, logistic regression has differences. But here you think about the very easy threshold, which is a step function. You say -1 and +1, essentially, right? So this makes it, let's say, the perceptron model. And let's see how that works when we just maybe have some training examples. Now you could think of that if we would have, let's say, this data set on the left-hand side, you have a certain training phase that you always put that in, right? Always this axis can be in. But the beauty is you see also the Y is given. So Y enables us, when it comes out, to always check, is it really correct? Or I have to change the weights. How I change the weights will be now something we talk about, which is a machine learning in it. But this is a machine learning model that could be potentially working if I find the right weights. And you see, when you stick in 0.3 as weights and then put the bias as 0.4, actually, this data set could be learned. And how you basically put it through and come to your label Y is just, this is sign, simple sign function that is very specific, of course, here for binary classification with the perceptron. But this is a training phase. You try it again, many times, 1,000 times. At some point in time, you have weights that work. Of course, this is a bit cumbersome for us. We want to have automatism, but you can stick it in and you see it gonna work. In some of the samples, if you just stick it in, you basically come to exactly that the equation is satisfied and the sign function. So how could we now automate this process? And this is something what is, of course, now the idea of thinking about the line again in the called decision space, right? So we call this a so-called hypothesis that depending on the weights and thresholds, there are many different hypotheses possible, right? In the end, I'm talking again that these steer essentially how your line looks like in the space and would differentiate the blue from the green dots completely different, right? So this would be playing now with essentially all of these different lines. And this is something what, of course, we can do by just, shifting it around in the space, but we need a principled way of doing it. For getting to there, we do some, let's say, mathematical short tricks just to get you a bit reminded about the transpose or what an inverted vector is and so on. So just for mathematical convenience, we could say that the threshold is also a way to learn when we just say that the threshold is 1 as the first item. So we put essentially W or the weight in W within essentially this kind of equation and say always the first data item would be 1 because I have to learn it anyway. And this is just for, let's say, the mathematical package, a more easier way of writing it. The more compact notation would be essentially what you see on the top. We have to add a transpose because both are vectors, right? And in order to make the vectors in a dot product working, we have to have one of those transpose, which is nothing else than turning a vector, let's say, in a column vector, for example, right? So this is what we play around with. Others could also say it's just a simple dot product notation. What you see here essentially is all the same. And you will find machine learning books talking about it, writing about it, and all of them look very similar. And some use the transpose notation, some use the dot product notation, some the long version. It doesn't matter. But it helps you maybe to connect to some of the elements. Still, the W's is, of course, what we want to learn now. And in the H's, the different red ones, will then determine when I play around with the weights, where exactly is a line in the space. Now, how that looks like now from the algorithm perspective is that I have to change apparently the line all the time in their orientation. And we need a principled way of doing it, still learning a bit from it when we do this. And this brings us to the Perceptron learning algorithm that you see here. Essentially, it uses our label that you know from Y, always every iteration. So it's an iterative learning approach, taking one sample at a time, putting it in the sign, and then comparing the sign with essentially the label that we have. If it's misclassified, we just add essentially the label to it and continue with this again and again. And of course, I just give a short update to this weight, which means in terms of vectors, you just flip it, right? Brought a small video to show you this, essentially how that works over time. Just come to this. So essentially, you see here the Perceptron learning algorithm in action, always changing the direction depending on what sample you need. And over time, you can show it actually converges if the data is linearly separable. That means if there's really a space between the red and the blue dots which are not overlapping. If there's just one point from blue in the red space or the other way around, it will not work. It will be always continuing. Right? It will not converge. But this is the simplest learning algorithm, admittedly from the 50s or 60s, basically beginning of the 60s, which still has essentially relevance today, which is still correct today, and shows you essentially now the essence how you could do a simple line classification. Of course, today we have much more advanced algorithms, but this is, let's say, now the principled way that you would do in the flowers. You put in all the attributes that we just have seen. You have W transpose X, and can always have the guiding label there because we know already from those 100 samples if it is an Iris setosa or an Iris virginica, right? And if you do this now 100 times, 1,000 times, it takes maybe to see that all of those are actually correct classified. You create this line in the space. Now, the point is we didn't do this for this 100 samples. We want to have new flowers. So if someone now comes with a new flower and measures the petal length and the petal width, on the top, we can directly classify it. Actually, it's much closer to the green ones, to this particular class of flowers than the other. And essentially, all different machine learning algorithms operate very similar in this regard. This is just, let's say, the simplest learning algorithm that you can have here. Now, just to fix some kind of terminology. So we have here, of course, lots of complex material. That's why I start also very, very slow. And I leave out a lot of things on the way, like validation data sets, cross-validation sort of things, and lots of statistical learning theory, which usually should become, now basically lecture after lecture if it would be a machine learning course. But of course, we don't do this here in the class. We keep it to a moderate degree. But I think you have seen that essentially doing this simple classification based on line is relatively simple. So let's reveal a little bit how we have done this. We had this labeled data set, which makes it supervised, right? So this is, of course, important. If you don't have the label, I don't know how to correct the line. It's hanging in the air. I can still maybe experiment of shifting it around, but it will be very volatile, unsupervised. I just shift it manually. Here, I have a principled way of doing it because I could use a label inside, the error measure to correct the weights all the time. That's why it's always adding a vector, subtracting a vector, adding a vector, subtracting a vector, until it's actually no misclassified point. Now, the goal also that you should always keep in mind in machine learning, that differentiates us usually from statistics. Statistics want to give data and say something about it. We are not interested in that. We want to have data to build a model that then predicts in the future, right? This is something, the capacity of a model, the learning model. Again, we would talk about Batnik-Schervonenkes dimensions, the feasibility to learn, learning theory. It would be 4, 5, 6 lectures in my machine learning course usually. But definitively, this is a really big thing. We don't do it just for memorizing the model. We want to have future unseen points right? The new flower that comes. We're not interested in just making it correct for this 100 flowers and say, 70 of those are from this type and 30 are from this type. It's just for us a helper to create a model for unseen data in the future. That's machine learning. Basically, you can remember it's the same like if you memorize everything from all the material, maybe it still doesn't help you in the exam, because exam you also here and there have to have some logic, some way of how you do it, right? Not just, having plain all the solutions and answers already put in your head. So in order to do this, we always differentiate between the so-called training set and test set. That will be in the second part of the lecture, much more eminent. I come to this, but it's important to think about that. Basically, you train on a certain set and then you put away a test set. And once you trained your model, you created your model, then you take the test set and test it if it's really good, right? So this is something what we'll also do more in the second part of the lecture. And of course, how you cut this is basically something you'd never know really. Sometimes if you're swimming in training data, then 10% would be a good idea to start from. Statistical learning theory needs also lots of training data. That means if 10% of your data is too little, you have to increase it gradually. Maybe also take different validation data sets and throw them in different corners. So it really depends how much data you have, but essentially it's good to keep, let's say, as much as you can for testing, because this is your real life test, right? That's where you get your check from the bank if you did everything correct. Just as a summary, and then we will look at some video as a motivation for the second part. We have now talked about linear classification, simple binary classification. We put that basically in this Perceptron model. We learned basically sum up the weights and, using our signals coming through again and again. And we use the step function. Now, when I would not use the sign function, I get a real value out, which people call linear regression. That's also what you can do. Trend analysis, right? Marketing, sales, more money in marketing means more sale, whatever. Now, what we want to do in the next part of the lecture is then logistic regression in the cloud. And there's also basically the idea that you have a very similar approach, but instead of using just a very, let's say, hard step function, -1, +1, if you remember, we have here the sigmoid logistic function, which is a bit smoother. This enables us also to play a little bit around with, let's say, an optimization technique called stochastic gradient descent, which we will talk about. And of course, it's an introduction to this topic. We have lecture 3, we have our assignment 1. We will learn this gradually. And then we pick it actually up also in lecture 6 when we start talking about neural networks, because the key ideas that you see here on this slide from the Perceptron and the modeling of this is actually the same how a neuron works in a neural network. Just different activation functions, rectified linear units today, not anymore tanh or sigmoid. So that's quite important. Right, and so I think that's all really I wanted to say in the moment. I think still the video has merit for everyone who has, let's say, done logistic regression a lot. Has someone used logistic regression here in the course? 1, 2, okay, that's all right. So I think the video is a very good summary, essentially. And it's important to understand then in the second part, the combination of logistic regression with the cloud. So let's look a little bit on the video. It's a bit a longer video, but it captures a lot of essence, which I usually would have maybe 2 or 3 lectures to talk about. So it's probably a good idea to just have this video today. Of course, online, if there are questions, please feel free to put it already in the chat.
Hey guys, and welcome to yet another fun and easy machine learning tutorial on logistic regression. To explain the concept of logistic regression, let's imagine that we want to classify whether a Pokemon will win a battle against another Pokemon. How would we classify this? Well, we could look at a set of features such as hit points, size of the Pokemon, attack rating, and defense rating. Now, intuitively, if your Pokemon has insanely high hit points, it would take ages for the opponent Pokemon to destroy yours, assuming the rest of the features are the same for both Pokemon. The same goes for size, attack, and defense of a Pokemon. So we can represent this using the equation below, where X is your features, B, also denoted as theta, are your coefficients. Now if we just take two features such as hit points versus size of a Pokemon, we can use an algorithm such as linear regression and threshold the output. But what if we had an anomaly where the size of a Pokemon wins even though it has low hit points and is small in size? This would lead to misclassification. Also, another problem with linear regression is that it also gives values larger than 1 and less than 0. And this is where logistic regression comes in. Looking at the background of logistic regression. So logistic regression is another technique borrowed by machine learning from the field of statistics. It is a go-to method for classification problems, despite the name logistic regression. It is not another algorithm for regression. Logistic regression is but similar to linear regression in a sense that they both have the same goal of estimating the values of parameters, coefficients. So at the end of the training of the machine learning model, we got the function that best describes the relationship between the known input and the output values. Unlike linear regression, the prediction of the output is transformed using a non-linear function called the logistic function. Some variations of this name are called the sigmoid function as well as the logit function. The logistic function, also called the sigmoid function, was developed by a statistician to describe the properties of the population growth in an ecology rising quickly and maxing out at the carrying capacity of the environment. This is an S-shaped curve that can take any real valued number and map it into a value between 0 and 1, but never exactly at those limits, also known as asymptotes. Looking at the logistic regression equations, so the logistic regression hypothesis is defined as h theta of x, which is a function of g theta transpose x, where function g is the sigmoid function, which is defined as g of x equals 1 over 1 plus e to the power negative z. Okay, so back to our Pokemon example. If we take the hit points as x1 and the size of the Pokemon as x2 for now, we plot our data as shown over here, where x's show wins and zeros show losses. We can draw a clear line, also known as the decision boundary, which separates the wins from the losses. From this we can estimate or predict with high certainty whether a Pokemon with a certain size or hit point values will win or lose. You may note that the gradient is quite similar to linear regression gradient. The difference is actually because linear and logistic regressions have different definitions of HFX. So the nice thing about logistic regression is that it can be used to fit complex non-linear datasets, which means we can build more complex decision boundaries by fitting complex parameters by using higher order polynomials. So how do we go about finding the coefficients of the logistic function? Well, we can estimate the values of the coefficients using stochastic gradient descent. We'll learn a little bit more about gradient descent and stochastic gradient descent in a future lecture. This is a simple procedure that can be used by many algorithms in machine learning. It works by using the model to calculate a prediction for each instance in the training set and calculate the error for the prediction. We can apply stochastic gradient descent to the problem of finding the coefficients for the logistic regression model as follows. So given a training instance, number 1, calculate the prediction using the current values of the coefficients, and 2, calculate new coefficient values based on the error in the prediction. The process is repeated until the model is accurate enough. For example, the error drops to some desirable level, also referred to as minimizing the cost function, or for a fixed number of iterations. So you continue to update the model for the training instance and correcting errors until the model is accurate enough or cannot be made any more accurate. It is often a good idea to randomize the order of the training instance shown to the model to mix up the corrections made. By updating the model for each training pattern, we call this online learning. It is also possible to collect up all the changes to the model over the training instance and make up one large update. This variation is called batch learning. A little bit more on that in a later lecture. If you look at the applications of logistic regression, number 1 is image segmentation and categorization, 2, geographic image processing, 3, handwriting recognition, and 4, we can use it for healthcare, where we analyze a group of over 1 million people for myocardial infarction within a period of 10 years is an application of logistic regression. We can use for prediction whether a person is depressed or not, based on a bag of words from a corpus, seems to be conveniently solvable using logistic regression as well as support vector machines, or SVM. The reason logistic regression is widely used, despite the fact of state-of-the-art algorithms such as deep neural networks, is because logistic regression is very efficient and does not require too much computational resources, which makes it affordable to run on production. Yes, your server won't crash. If you look at logistic regression compared to decision tree, so both algorithms are really fast, and there isn't much to distinguish them in terms of runtime. Logistic regression, however, will work better if there's a single decision boundary, not necessarily parallel to the axis. Decision trees can be applied to situations where there's not just one underlying decision boundary, but many, and will work best if the class labels roughly lie in a hyper-rectangular regions. Logistic regressions is intrinsically simple, it is low variance, and so is less prone to overfitting. Decision trees can be scaled up to be very complex and are more liable to overfitting. Pruning is applied to avoid this. Okay, so that is it. Thank you for watching. Please don't forget to like, subscribe and share. Click that bell icon to get notified of more fun and easy machine learning algorithms. Also, animating these videos takes a lot of
Yeah, so essentially we will pick up in the second part of the lecture really all what was discussed there, here and there. So don't worry if you didn't really catch everything from this video. It was just used to motivate you and warm up a little bit with some interesting drawings. And of course, with a good speed to be basically put again on the table in the second part of the lecture. So I think we break here for 10 minutes and then come back to the second part in the clouds.